Okay, this is seminar number 4 in the winter quarter. And today we have Professor Ching-jae Lee, who is an assistant professor in bioengineering, giving a talk with the title of Structural and Functional Imaging Using Low Coherent Interferometry. You're changing the title. Dr. Lee got his BS degree in applied nuclear physics in China, University of Science and Technology of China in 1990. And then he got his PhD in biomedical optics from University of Pennsylvania in 1998. And he did the 3-year postdoctoral research at MIT in electrical and computer engineering. And then about 17 months ago, he came to University of Washington as an assistant professor in bioengineering. His research is mainly in the optical imaging technology development and spectroscopy development and their application in biomedicine, various areas of biomedicine from imaging side to diagnostic side and even the molecular contrast agent side. So he has a wide-ranging interest in imaging and instrumentation in optics. And last year, he was voted by students as the 2001-2002 Teacher and Mentor of the Year award, which was very unusual as a first-year faculty member in the department. So Dr. Lee will give us a presentation with imaging, structural and functional imaging. Okay.
Thank you, Professor Ken. So I just realized, time went by so fast, almost like 16 or 17 months has been passed since I first came here. But anyhow, today I'm going to talk about structural and functional imaging using a technique. It's called low coherence interferometry. So if you use, you can use this technique for a variety kind of applications. There are a variety kind of variations of using how to use this technique. If you use this technique, LCI, and to do cross-sectional imaging, for example, you look at an image which is perpendicular to the surface, tissue surface, which is different from histopathology. And in that particular case, we have a special name, and that is called optical coherence tomography, or OCT for short. So today, I'm going to mainly focus on OCT rather than the broad area of how we can use this low coherence interferometry. So to begin with, I'm going to first briefly talk about why we need high resolution for biomedical diagnostics or for monitoring, etc. And then I'm going to briefly discuss the working principle of OCT and some technical parameters of optical coherence tomography, which use the low coherence interferometry as the basic working principle. And then I'm going to switch to talking about enabling imaging probes, which allow us to image the internal organ or systems. So for example, for any imaging modality, if you can do whole body imaging, then that's okay. Otherwise, you need special probes to deliver the signal and to detect the signal back from the biological tissue. And then I'm going to talk about another effort, our current effort, try to push the digitalization, not a digitization, it's digitalization of the system. Basically, the means try to convert the analog components and to use digital approach to perform the same task as those which were performed by using analog components. And this will give us a certain flexibility, for example, speed, system miniaturization, and we can extract other information such as Doppler flow or spectroscopic information in real time. And at the end, I'm going to talk about some examples of biomedical application of this technique. So why we need high resolution imaging for diagnostics? So here I just show you one example. For example, many diseases during the development manifest themselves by the structural morphological changes. And here shows the normal tissue, basal membrane, and those epithelial layers, for example. If you look at those cells, they're pretty uniform. So however, for the case of early cancer, some of those cells become abnormal. That means if you look at those nuclei, they have different kind of shape. And the size is different, the cytonuclear to cytoplasma, the NC ratio start changing. And as time goes, more and more cells become, that fashion becomes more irregular, for example. And at a certain point, those tumor cells or cancer cells can break the cell, can break the basal membrane and become invasive. And then as time goes along, those cells might break the blood barrier and go into the bloodstream, and then metastasis starts. So, however, if we can detect the process, those morphological changes at early stage, we might be able to treat this disease early on, for example, using surgical procedure or some other recently developed procedure, such as ablation, either using light, heat, or RF frequency. So another example is in the heart, in the cardiovascular system, and in particular for the rupture-prone plaques. So normal blood vessel has a very nice layer structures such as the intimal, which we can see clearly, and then the media, and then the adventitia, the connective tissue around it, which it doesn't show here. Those are just a cartoon type illustration. But for rupture-prone plaque, and you will find there's a lipid core, necrotic lipid core within the vessel wall, and then on top of it there's a very thin fibrous cap. So as the lipid core develops, and this cap becomes thinner and thinner and thinner. So at a certain point around the shoulders, it might break. And then thrombus or thrombi will form if this is big, the blood clot is big, and then the entire artery can be blocked. For example, if this happened in the coronary artery, and it can block the blood supply to the heart itself, and then it causes acute heart attack. So one thing is, as I said, why we need high resolution. The thin fibrous cap, if we characterize it as rupture-prone or vulnerable or high risk, and the dimension, the length scale is about 5 to 60 micron, the thickness. So it's very thin. And in order to detect that, you do need some technology which has the resolution better than this. So here are just a list of a variety of different clinical diagnostic or imaging modalities, such as plain X-ray, X-ray CT, PET, MRI, ultrasound, and the last one is optical method, which is going to be the focus, in particular the optical coherence tomography of this talk. So each one has their own niche. Each one has their own niche. Some of those are invasive, and some of those are non-invasive. If you look at the resolution, starting from the top, and it varies from a few millimeter all the way down to 70 micron, for example, the clinical ultrasound, the CEDAR's clinical ultrasound, which has 40 megahertz. Of course, the frequency can be as high as gigahertz, right? So, but the penetration depth is, there's another issue. And then some of those techniques are only sensitive to structural information, but others might also sensitive to functional information, such as oxygen information, or water, for example, or blood flow. For optical technique, the contrast is really from the absorption coefficient, the absorption and scattering, the optical absorption and scattering. And it's also sensitive to fluorescence, the phosphorus, and also sensitive to birefringence, meaning if it's sunlight to tissue, and depending upon the polarization, which axis, which direction your electrical field oscillates, and then what you detect, the signal might depend the orientation or the incident light polarization. So now let's just briefly go through what is the working principle of OCT. Some of you might already know or are very familiar with ultrasound. So OCT, you can think of it as just optical analog of ultrasound. And the working principle is so similar. Suppose I have a pulse. Just have a pulse. Then I can send this pulse to tissue. And at different layers, different structure, the boundary with the structures, and the pulses will be bounced back. So what we try to do is to detect the echo delay here, as well as the intensity, the amplitude of the echo. But however, light is so fast, travels so fast, 10 to the 3 times 10 to the 8 meters per second. It is so fast, and so therefore, in order to detect, it's almost impossible to detect echo delay time using electronics. Therefore, we use a technique is called low coherence interferometry to detect the echo delay. And again, how we do it? The heart of this system is basically the essential component is Michelson Interferometer. If you're not familiar with that, let's just think about we have a piece of glass. Okay, what it does, if you send a beam to it, it can split. It can split the beam to two parts. So just like here, we send a pulse to it, and this beam splitter can split the pulse once 50% sent to the sample, another 50% sent to a reference arm where you have this little mirror. So the mirror going to send the reference pulse back, and then the pulse, the echoes from the sample going to be bounced back and recombined by this beam splitter, a piece of glass, if you can think, if you like to think about that way. So if those two pulses, if they travel over the same distance here and there, and then they will overlap at the detector. Since those two pulses are split from the original one single pulse, you can think about that way, and then they will interfere. If they don't overlap, they will interfere. So another way to think about, at the detector, if you see an interference signal that tells me the pulse travels in the sample arms, travels over the same distance as the one in the reference arm, which you know how much the distance the light should travel in the reference arm. So therefore, you pick up the pulse. Whenever you see an interference signal, you pick up pulse from the sample which travels over the same distance as the one in the reference arm. By moving this mirror back and forth, basically you change the reference path length, and you can pick up the pulses from the samples, back reflected at different depths. If you look at the OCT signals, the interference signal is shown here. It's more or less like the radio frequencies, an amplitude modulated signal. It's isolated, and the full width half maximum of this signal gives you the so-called the depth resolution. Another way to think about, to get a better depth resolution, you would like to have a pulse which has a very, very narrow path width in time domain. So the narrower, you require more accuracy for those two pulses to overlap. So that determines the resolution. And another thing I want to mention is the heterodyne detection. As the interference for interference signal basically is the product of the sample signal, the signal we're interested in, and the reference arm signal. So really it's the product as shown here, right? And the reference signal, you can control that, which in general is pretty big. And to detect the signal we're interested in, the sample signal, the signal from the sample is very small. But however, what we really detect is the product. This like amplifier is optical amplification. And this amplification in general is huge. It's much more than you can do in general using electronic components. And using this so-called heterodyne detection technique, we can achieve detection sensitivity down to 100 minus 20 dB. Actually, we just got even this here just lists minus 10. But in the lab, we can do easily up to 100 minus 15 or minus 120 dB. So, and then we can plot it at the echo intensity versus the echo delay time and form an axial scan. And we can scan the beam laterally, cross the tissue, and form multiple adjacent axial scans. You put them together, and you plot the logarithm of the intensity, the signal, versus depths, and put them together to form so-called tomographic image. Remember, this is the surface of the tissue, and this is deep into the tissue, which is opposite from the histopathology, which you do is on-fast imaging. So histopathology, you look at the on-fast imaging, meaning the imaging plane is parallel to the tissue surface. But this case, the imaging plane is perpendicular to the tissue surface. So here are just some key parameters. For example, for any imaging technology, we ask ourselves, what is the resolution? How are you going to improve your resolution? What determines the resolution? In this case, and the resolution is very interesting. For OCT, the axial resolution is determined by the light source. I'm going to talk about a little more in a few seconds. And the light source we can use for this kind of technology includes femtosecond lasers, really short pulse, SLD, superluminescent diode is a different version of LED, and continuum generation using nonlinear optic process, which we will not talk about the detail. And of course, another parameter is how fast we can do imaging, right? In order to remove or reduce the motion artifact, we are hoping we can really do real-time imaging fast. That means we can change optical path length. You remember in the reference arm, the little mirror moves that in real very, very fast. And in order to move this technology to clinical situation, certainly we're going to ask ourselves where we can put the patient, or how we can deliver the light to the patient, one way or the other. So that means we need a certain platform, such as imaging probes. And in general, those probes have to be small, such that we can deliver to the internal organs or systems, such as the GI or the respiratory tract. And then at the end, I'm going to talk another aspect with this technology. Right now, people are trying very hard to digitize the entire system, basically, convert the analog component into a digital component, and which is going to give us a certain flexibility. So one unique feature of OCT is the resolution, meaning the coupling of the axial resolution, the depth resolution, with respect to the transverse resolution. So for OCT, the depth resolution, it really depends upon the light source, depending upon how short the path width is. Or another way to look at it is how broad the spectral frequency spectrum is. So 1/T gives you, if the shorter the time is and the broader the color, the more the color you have regarding light. So, and here just gave you, the depth resolution is inversely proportional to the spectrum bandwidth. The more color you have, and then the better the resolution. So, and the transverse resolution, the lateral resolution, is the same as in microscopy. So basically, it depends upon how tight you focus the beam. The tighter you focus the beam, the smaller the spot size, and then the better the resolution. But we can decouple this, which is different from confocal or two-photon, etc. So the principle is very simple. Here, just briefly go through what kind of schematic, what kind of system we can set up. And since we're using light, we can use fiber optics. So therefore, the entire system can be quite compact. First, we need a light source. And then we need a so-called fiber coupler. We couple the light source into a beam splitter. It's just like the piece of glass, but this was done in fiber optics concept. And the beam splitter going to split the beam into two arms, one to the sample arm, reference arm, where we have this little mirror to move back and forth. Another goes to the sample arm, where you have a variety of kind of imaging systems or imaging probes, delivery probes. And then the light coming back from the reference arm and the sample arms recombined in the so-called fiber coupler, and then, well, we can skip that, and then sent to the detector. And then the beam can also send it back further. We look at another detector. So there are two detectors here. And well, without telling you the detail, I'm just going to tell you those two detectors going to pick up both the AC signal and the DC signal. AC means the interference signal. But however, for the AC signal, the interference signal in those two detectors, they are 180-degree out of phase. That was done by using this optical technique. And then when you add those two together, you can subtract those two together. What you end up with, you basically double your AC signal and you remove your DC signal. And this is so-called the double dual balance detection, which is widely used in telecommunication. And then you send everything to amplifier, bandpass filter, etc., and demodulator, and you store the data signal into a computer and display it. So that's basically the system. So it's still very compact. Now here, just to show you one example, what we can do. So using this kind of technique, we can image, for example, in vivo of a hamster cheek pouch. If you look at the top layer is epithelial, and then the lamina propria, and then multiple those muscle layers. And here you also see a blood vessel, and blood is highly scattering. Therefore, the attenuation is extremely high. And the scale bar here represents 100 micron. So as I said, one important component or component with this technology is the imaging probe. In order to say something inside the organ, such as the GI tract or the cardiovascular system, we need a small probe which can deliver the light into that system and collect the light back and send out to the body and to the computer detector. And this is kind of the probe which was developed quite a few years ago. Here, just to show a schematic. It consists of a single mode fiber, a very small focusing lens, and then a prism directs the light by 90 degrees. So the light coming in through a single mode fiber and then bend it by 90 degrees. And what you can do is you scan the beam, you move the catheter back and forth to do so-called linear imaging, or you can scan the beam circumferentially to do a radial type of imaging. You can do either way. So the catheter is so small. For this particular case, it's about 1 millimeter. But right now, we can make the catheter down to 350 micron or even 250 micron. So apply that to a cardiovascular system is not a problem. And since it is so small, it can be interfaced with a variety of existing medical instruments, such as endoscope. Just go through the accessory port with endoscope, and you can, do dual modality imaging. So with one, help another. Here, this slide I showed many times before, where we look at the esophagus. This is a normal human esophagus. You see all those very nice intact morphologies, the epithelial layer, lamina propria, submucosa, etc. And if you move towards the pathologic ones, for example, the Barrett esophagus, caused by, for example, related to the heartburn, chronic heartburn, or gastroesophageal reflux. So you notice those layered structures, those morphologies are disrupted. Instead, you see those low reflection pocket. Dark means high reflection. You have strong signal coming back. White means there's no signal coming back. And the pocket here represent a glandular. If you put this catheter, move the catheter right on top of the Barrett, you see a purely glandular structure. You don't see those very nice intact layered structures, the morphology. So one very interesting Barrett's. Well, here just mentioned, 1% of men over 60 years, age over 60, will develop Barrett esophagus. And 5% of the population will heartburn or GERD disease. Okay, they will develop Barrett esophagus. For those patients, the population who have Barrett esophagus, and they have 30 to 50-fold of increased risk of developing esophageal endocarcinoma, cancer. And recent study has shown that in the past 2 decades, the esophageal cancer has increased, the cases has increased by almost 350%. So, but the good part is some treatment, the treatment methodologies are becoming available. For example, you can ablate the Barrett esophagus using light or heat, coagulate the tissue. And then a new tissue, so-called squamous epithelium, will regrow. But however, you don't know how much you ablate it. Sometimes there's certain residue of Barrett esophagus, and then can still develop underneath the apparent normal tissue. And this so-called Barrett, residual Barrett esophagus under the neosquamous, newly developed Barrett squamous epithelium, which is normal, you cannot see the Barrett under endoscope. Then what we can do? So one way to do it, using our technology, probably we can see something behind the surface. But however, in order to screen, to survey the entire esophagus, we need a tool allowing us to systematically imaging the entire esophagus. And one way to do it, one challenge is how we can stabilize the esophagus. And also, the esophagus is large. We have to image over a really large distance. And then how are we going to do that? So all this requires to develop a so-called a balloon type of catheter. And that's what we're currently working on. A balloon catheter basically has dual lumens. For the inner lumen, we have this small catheter, can go through it, has a really long working distance, about 8 millimeter. And then the outer lumen, you can inflate it. After you deploy it into the patient, you can deflate it using saline or air, and then stabilize the esophagus. But again, the challenge is, in order to see something far away, you need either, and with a small spot size, focal spot size here, to get a higher transverse resolution, and then you need the optics to be pretty big. But we cannot afford to have a big optics here. Otherwise, the entire catheter cannot go through the accessory port or endoscope. So the footprint we're looking at, we're targeting, is about 2 millimeter or so. Then how are we going to resolve this issue? So one way, like I said, in order to achieve larger working distance, you need large optics. Another way we recently find out, well, we can still use a small optics, but we focus the beam very tight at the very beginning. And then we can fully utilize the aperture. In other words, we can increase the numerical aperture. So by doing that, we can reduce our catheter optics from almost 2 millimeter down to 1 millimeter. Here just shows you how we can do this. But the bottom line is that by doing this kind of trick, we can reduce the catheter size from 1.8 to 1 0.0 millimeter, and the working distance, meaning the focal point with the beam, is about 8 millimeter away. That's about the size of the esophagus, the radius of the esophagus. And then the transverse resolution will not be compromised. For example, we can still achieve about 40 micron transverse resolution. So far we have been talking about a catheter which you can do this kind of side viewing, the so-called transverse imaging. So what about forward viewing? Meaning you can see something ahead of time before you really reach that point, which is in general very important. So, and again, the challenges there are size, how you're going to scan the beam. In order to do imaging, we have to scan the beam. How are we going to do that? And to keep the entire size small, catheter size small. So, and here is another approach we're currently developing, is using PZT, piezoelectric actuator, to move a small, very tiny focuser, or micro imaging probe. And this micro imaging probe includes a single mode fiber, and then we can thermally fuse this micro imaging lens to the single mode fiber. So the entire imaging probe is about 200 or 120 micron. But the big size, the big footprint is limited by this piezo actuator. But again, we are able to achieve 2.1 millimeter diameter, overall diameter. Here just to show some examples and postdoc in my lab, Dr. Liu developed recently. And this is a PZT actuated small imaging fiber. We can do forward imaging. We can scan in the X direction or the Y direction or at the same time. So you can do line scan or you can do a 2D scanning. And if you assemble everything into a protective tubing, this is what it looks like. And there are two parts. This part has a cap, like a window at the very beginning. So the entire footprint you can compare with this lens scale, 1 millimeter lens scale. So the entire overall OD, is about 2 millimeter. And here, just a comparison. If you put this little scope on a little penny, and this is not a penny, a dime. And then you can scan it. And you can scan it very fast, and the scanning frequency depends upon how long the fiber, this micro imaging lens is, inversely proportional to the L square. L is the length of this scanner. And right now we can scan at about 2.5 kilohertz and to achieve 5 frames per second imaging. And of course we can use, well, where are we going to use it? One area is the GI, another is the lung, etc. So now let's switch gear and talk about functional imaging, basically focus on Doppler flow. And I guess I do not have to overemphasize why we're interested in flow. For example, you probably want to know the flow to know something about the tissue perfusion, the oxygen perfusion, for example. And you probably want to estimate the burn depth, skin graft, whether it's live or something happening. It's the wound healing process, for example, and angiogenesis, for example, which involves in tumor development or in even engineered tissue growth. And also another application is in the cardiovascular system. If someone has a narrow artery, you try to expand it using stenting technique. And then the big question there is how much blood flow you really get after you stent it. If it doesn't improve much, and why bother, right? That's one area we need this kind of technology. So traditional approach is done to do Doppler imaging in optics or ultrasound. Was done using hardware. So it requires so-called the in-phase quadrature detection, etc., or polarization for light, polarization detection scheme. And what we're doing here is whether we can remove all those electronic components and then just use a digital approach. And that will hopefully give us a flexibility. To do that, in order to tell you how we approach this problem, just briefly talk about what kind of signal we're looking at. For OCT signal, this is how it looks like. You have this modulate signal. It comes here, and probably you don't see anything here, and then it comes in another place, right? Analytically, we can write this as amplitude and then cosine times the cosine function. And in the cosine function, there's a phase, and there's also a fast oscillating term, and that is called carrier frequency. They're also very fast. And this amplitude and phase are also, A and phi are also time dependent. They're also time dependent. But they change much, much slower compared to the so-called carrier frequency. So one way to do it and to find out whether we have flow or not is to find this phase, because when you have flow, the flow is going to change the frequency with the light, and they're going to change the phase, so-called the Doppler effect. So how we can achieve the phase? So one way to do it in optics is well known. We're given this X of t, the measured OCT signal, we can compose a so-called complex analytical signal, and that is given by ZT. The real part of ZT is the signal we measured. And what about the imaginary part? Well, the imaginary part, Y, turns out to be is the Hilbert conjugate of the measured signal. So, for example, if xt follows the sine, cosine type of function, and then the yt, the imaginary part, follow about the sine type function. It's just a 90-degree auto phase. So therefore, if we can measure the signal x of t, and then somehow if we can recover the analytic signal, complex analytic signal, z, and then we should be able to find out what is the amplitude and what is the phase. When we find the phase, we know what is the frequency shift, and then further to deduce what kind of flow we get. So one way to find ZT is, well, in order to find that in time domain, see what happened in frequency domain. Do we know the spectrum? Lucky enough, we know that the spectrum of this analytic function is related to the spectrum of the measured signal. And for the positive frequency part, they are the same. But for the negative frequency part, and the analytic frequency is just all zero. So that's the property of so-called Hilbert transform. So therefore, everything turns out to be very easy. We measure x of t, and then we take the Fourier transform. We get the spectrum. We throw out the negative frequency part, and we end up with a spectrum for this analytic signal. And then we can take an inverse Fourier transform to recover the time domain analytic function, which is shown here. So, and after we have that, we can clearly to extract the amplitude and the phase information for some of the amplitude and phase, the amplitude given by the square root law, and the phase, which is shown to be phi here, given by the arctangent. Here, just the flow chart. We measure the OCT signal, which is x of t. This is the real signal, and we take the Fourier transform to find the spectrum, fast Fourier transform f of t, and then we throw out the negative frequency, and we keep the positive frequency and take the inverse of Fourier transform to recover ZT. And then we recover both the amplitude and phase. So after we have the phase, there are a variety of different approaches, and to allow us to recover the flow. So here, we recently just did some computer simulations. For example, we directly program the Pentium chip in collaborating with Dr. Kim's group. Oops. And then suppose we image a tissue phantom, and like with a dimension 2 by 3 millimeter, and then we have a vessel which has a 400 millimeter diameter. Within vessel we have pulsatile flow, and the average flow ranges from 0 all the way to 1.4 millimeter per second. And then see if we can recover the flow, and then we take imaging. For example, to achieve, right now we can digitize the signal at 5 megasamples per second. For this particular case, we focus one line, say we have 10,000 data points, and the current performance using this approach, digital approach, we are able to perform one single line to recover the flow information within less than 2.5 milliseconds. And here, basically, just to show you. Oops. Suppose we have that kind of data, how we can recover this. This is about 4 frames, and you notice the intensity change that represent the pulsatile flow. And of course, this data is a similar data and has no noise. So what happens if I have 5% noise? And of course, you clearly see there's some noise in the background, and the flow is not that clear. In this case, we can also implement a Butterworth filter, second order, because it's digital, and it doesn't change the timing. It doesn't cost much computational power at all, but the image looks much better. All right, so I think I'm gonna just briefly talk about one application, and that's wound healing. So why we're interested in wound healing? In particular, cutaneous wounds. Cutaneous wound is very common. in clinic. So about 1.25 million people in the United States have burns per year. And more than 6.5 million people have chronic skin ulcers, especially for those people who have diabetes. Healthcare cost is very high. So how we assess wound healing in current state? Clinically, just by observation, visual observation. We don't know what's going on underneath, what we can see on the surface. But that really depends upon the experience. It varies between doctors and doctors. So, and the delayed assessment of wound can cause unnecessary morbidity. For example, amputation. So, in order to say how we can, one parameter we want to know what kind of process we can really detect using this high-resolution imaging technology. To know that, first let's go through briefly, what kind of process it is for wound healing. Suppose we have a full thickness wound, and the first thing happen is clot formation, due to those neutrophils or platelet. So after a few days, you will notice the epithelial layers, those cells, will migrate from both sides of the wound and try to bridge the wound. If this happens, that means the wound is healing. If this doesn't happen, you have to take another more aggressive approach to treat it. And then later on, it involves tissue remodeling or collagen collagen remodeling. But what we're really interested in are the first few days. So using a guinea pig skin model, we try to say if this technology can be applied for monitoring the wound healing. Here's a normal skin, guinea pig skin. The reason why to use a guinea pig is because the skin looks more or less like a human, more similar, very similar to human skin. And you can see the top layer is epidermis, and here the EV junction, not quite clear, and this is a corresponding histologies. And this is for day 1, meaning 24 hours after the wound was introduced. And you notice the clot formation. The OCT image here, very dark and very highly scattering due to those dead cells. And then about 3 days later, you notice our OCT is bridging with this epithelial cells. And this is confirmed by histology. So this basically tells us that this wound is healing. This is really like a preliminary. Of course, there are many parameters which affect wound healing, such as nutrition, like vitamin C, and metabolic status, or circulatory status. For example, for healing wounds, you require certain oxygen. So therefore, we are able to incorporate a so-called spectroscopy technique, optical spectroscopy technique, or near-infrared spectroscopy technique, and combine that technique with this imaging technique, providing not only the structure information as well as oxygen or oxygen saturation information. And another very interesting aspect is that the wound healing can be promoted by a variety of different kind of growth factors, such as the plate-derived growth factor, FGF or VGF. So you can put those growth factors on the provisional, say, hydrogel matrix, and you will release those growth factors control rate. But then the question is, what kind of rate, what kind of concentration? So maybe we can combine this, and hopefully it will give us some interesting results. And another twist with this application is tissue engineering. It's monitoring the growth of the engineered tissue. So this technology, since it's non-invasive, it allows us to monitor the healing process continuously or repeatedly. You don't have to sacrifice it. So therefore, this can potentially remove the fluctuations if you require a lot of animal studies and you sacrifice the animal at each time point. But by using this technology, you don't have to do so. And in summary, this technology becomes emerging biomedical imaging modality, which has application not only in clinical diagnosis, hopefully for biomedical, basic biomedical research. It can be applied for a variety of organs or systems. I didn't talk about like for ophthalmology, and the technology for imaging the retina has been commercialized. There are like more than 1,000 different units. More than 1,000 units have been out in the hospitals. And another feature of this technology, we can potentially combine the molecular imaging technique with this technology. For example, you can develop a certain kind of contrast agent. Right now, this is too preliminary to talk about it. But suppose you can develop a certain kind of contrast agent which can target specific, such as antigen, for example. And this kind of contrast agent going to provide not only absorption, but also fluorescence or scattering nanoparticles, for example, contrast for imaging. And another aspect with this technology, we can potentially combine the imaging technology with so-called mis-scattering. What end up with, we can not only get a picture, but we also can get a quantitative information about the scatter size, mainly the nuclear size. Why we're interested in that? Because of early or pre-malignant cancer, the nuclear size tend to be larger. If we can pick up that information, that probably allow us to be more quantitative to get an information about, well, to grade, say, if this is a pre-malignant or it's a malignant or invasive already. So at the end, I would like to thank my team members and Dr. Leo Michael and Michael Cobb and Reber Seriani and other students in our group. I will also acknowledge my collaborators at this campus. At the end, I would like to acknowledge the funding agencies from NIH, Whittaker, and the AHA. Thanks very much.
Okay, we have a lot of time for questions.